An optimization problem is an application of calculus to a physical situation where I want to make certain quantity as large as possible or as small as possible. Here is an example. I want to build an open box that will have 4 side walls and a bottom but no top, with a square base. The volume of the box must be 500 cubic centimeters, and I want to spend as little as possible on the materials. What dimensions should I choose for the box? At this moment, I invite you to pause the video and try to solve it before you continue watching. Even if you cannot fully solve it, my explanation will be much more useful if you spend some time trying to understand the statement and setting it up. First, we need to model the problem. That is, we want to convert the word problem into a precise mathematical question. In this case, I'm looking for a question of the form, I want to find the maximum or the minimum of this specific function on this specific domain. And figuring out what that function is and what that domain is the modeling part of the problem. This is what the box may look like. I'll begin by giving names to the dimensions of the box, since that is what the problem is asking about. I'm going to call x this side of the base, and since the base is a square, x is also the length of this side. The height is a different dimension, so I'll call it y. In this question, I want to spend as little as possible on the materials. What that means is that I want the total surface of all the 5 walls I'm building to be as small as possible, because that will use the smallest possible amount of material. So I want to minimize the total area. I'm going to call the total area S for surface. So let's figure out what it is. First, we have the bottom of the box. And the bottom of the box is a square, and is a square with side length x, therefore the area here is x squared. And then I also have the other 4 walls. Now let's look at the right wall, for example. Here the base is x, but the height is y. So this wall has area x times y. And the same is true of the wall on the back, and the one on the left, and the one on the front. So this adds 4 times xy to the total surface area. That's the quantity I want to minimize. However, x and y are not independent variables, they are related. There is an extra constraint because we want the total volume of the box to be a fixed quantity. We want the total volume to be 500 cubic centimeters. Now the volume of a box is the product of the 3 dimensions, so it's going to be x times y, or x squared y. I think I should also say that x must be a positive number and y must be a positive number, otherwise the problem doesn't make any sense physically. And that's it. Now I have a function with 2 variables but with a constraint. I find it easier to calculate the maximum or the minimum of a function with a single variable without constraints. And one way to attack this is I can use this constraint to write one of the variables in terms of the other. In this case, I think it's a bit easier to write y as 500 over x squared. And then I can use this and plug it in the original expression for the surface area to get s in terms of x and x only. If I do that, I get that s is going to be x squared plus 4x times 500 over x squared, or we can simplify that as x squared plus 2000 over x. And there is my function. My goal is to find the minimum of this function. And this is in the domain when x is any positive number. That's the only constraint I have now that I have removed y. Now that we have set up the problem, the second part is the easier part. Use calculus to find the minimum of the function on the correct domain. This function is differentiable on the domain, so to find the minimum, I'll look at when the derivative is 0 or positive or negative. The derivative of s with respect to x is going to be 2x minus 2000 over x squared. Now, I'm interested in when this is 0 or positive or negative, and I find it easier if I reduce to common denominator. I can also factor a 2, and in the top I get x cubed minus 1000. And once I put it this way, it's clear. The derivative is 0 exactly when x cubed is 1000, or in other words, when x is 10. That's the only critical point. At this point, I know many students like to stop and say, therefore, that must be the answer. But we cannot do that. This is the only critical point, but we're looking for the minimum, not the critical point. Perhaps it is the minimum, perhaps it is something else. Perhaps the function doesn't even have a minimum. So we have to do a little bit more justification to say why the minimum occurs there. What I'm going to do is look at how the function behaves to the left and to the right of 10. I know that at 10 the derivative is 0. Now when x is greater than 10, the derivative is positive, and when x is smaller than 10, the derivative is negative. Therefore, the function s is decreasing all the way to 10 and increasing all the way after 10. And now, yes, with this information, I know if the function is all the way decreasing and then all the way increasing after, then it must look something like that. And therefore, at 10, definitely, I need to have the minimum. Not a local minimum only, yes, the global minimum, which is what I was looking for. So after doing this little justification, then I know I have found the answer. And therefore, my answer is x equals 10 centimeters. And remember, I also need the other dimension. Y was 500 over x squared, which comes out to be 5 centimeters. And these are the dimensions that I need to use in my box in order to spend as little as possible on materials.